So I'm just going to try and run through those questions. So we have this okay. All right, so I hope you can all see what I have here. The question says, consider a 3-meter high, 6-meter wide, and 0.3 meter thick brick wall, whose thermal conductivity is K equal to 0.8 watts per meter Kelvin. On a certain day, the temperatures of the inner and outer surfaces of the wall are measured to be 14 degrees Celsius and 2 degrees Celsius, respectively. Determine the rate of heat loss through the wall on that day. Okay, so this looks like from initial examination. This is a conduction problem through a wall. And as we talked about last week, conduction can be considered in multiple ways. So the first thing you have to think about is, am I being asked to solve a multi-dimensional question? Is this a transient or steady state problem? Is the thermal conductivity constant? Can you consider these three factors before you move ahead? And if we look at this, there's nothing here to suggest that this is a transient problem. Okay, it's not changing with time. We don't have any time factor in the question. So we can assume steady state conditions. And also, the geometry of what has been described here doesn't suggest that we have to consider a multidimensional heat conduction. So we can also assume that this is a one-dimensional problem. We can also assume that the thermal conductivity is constant and is determined by the value of K that has been given. Okay, so if we make all the simplifications, then we can use Fourier's law of thermal conduction to solve this problem. And if you remember, we have Q dot is equal to K A T1 minus T2 over L. Now, once again, remember that the minus sign is not there because I've flipped T2 and T1, okay? So first of all, let's try and compute let me set this aside. Let's compute the area, okay? We're given values, it's 3 meter wide, width is 3 meters. We have, 6 meter wide, 3 meter high. The height is 3 meters. And then the wall is 0.3 meters thick. So our area was simply 6 by 3, which is 18 meters. So our area will be 18 meters squared. Okay. We are also given K to be 0.8 watts per meter Kelvin. Okay. Now, I'm going to go ahead and put these values in our equation. We are also given, we also have T1 to be 14 degrees Celsius and T2 is equal to 2 degrees Celsius. Okay. L is the thickness, which is 0.3 meters. So we have everything we need to evaluate the rate of heat lost through the wall. Okay. So I'm just going to put this down here now. Q is equal to 0.8 watts per meter Kelvin. At this point, I'll say I want to point something out. I advise you to always write the units when you're computing your values in heat transfer or thermodynamics, because it helps you know if you're mixing up different dimensions of units. Okay, because sometimes you can be given these units in centimeters and meters and millimeters, and you want them to be uniform. Okay, so this multiplied by 18 meters squared, we have meters, meter, so we're good. And then multiply by, now, there's this thing with conduction that does not apply to radiation and sometimes convection. When you're calculating conduction, it's a temperature difference. So it really does not matter if you convert from Celsius to Kelvin, okay? Because it's a difference. If I convert this to Kelvin, I will still get the same temperature difference value. So although we have watts per meter Kelvin here, I don't have to convert this. As a matter of fact, in some textbooks, you will see 0.8 watts per meter degree Celsius. Because for conduction, it's a temperature difference. But don't make this mistake when you're dealing with radiation, because it's not a temperature difference. Okay, so I can afford to say 14 minus 2 degrees Celsius here, and everything will be fine. Okay, this only applies to conduction, and divide this by 0.3 meters. Okay, so it's that simple. If you compute this, okay, we have 0.8 multiplied by, compute temperature difference first. So this is 12 divided by 0.3 multiplied by 18 multiplied by 0.8. Okay, we get our answer to be 576 watts. So that's a pretty simple way of evaluating heat loss through the wall. This was a pretty simple question. Okay? I doubt the professor will give you a question this simple in your exams, but so that's how you solve it. Now, professor also asked me to simplify one of the questions in your homework. Question 3. So this is a question that you've been given. Now, it says a 4-meter high, 6-meter wide wall consists of long 18 cm by 30 cm cross-section of horizontal bricks. Okay, and the horizontal bricks have the thermal conductivity K given there. And these are separated by 3 cm thick plaster layers, each with that thermal conductivity. There are also 2 cm thick plaster layers on each side of the wall, and a 2 cm thick rigid foam. okay, on the inner side of the wall. Now the indoor and outdoor temperatures are 22 degrees, 22 degrees and -4 degrees Celsius. And the convection heat transfer coefficients of the inner and outer sides are H1 and H2 are given respectively. Now, assuming one-dimensional heat transfer and disregarding radiation, determine the rate of heat transfer through the wall. Now, in order to solve this question, you have to find the um, resistance, thermal resistance in the materials, and it's a composite wall. You've been given different materials, so you have to evaluate the equivalent resistance that the entire wall gives you. Now, I'm not going to solve the entire problem. I will just simplify the how to evaluate the cumulative resistance. Okay. Now, you've been given this question, so I'm going to assume you've done this in class, where you can represent the thermal resistance in the wall by the in the same way as we do resistors in an electric circuit. Okay. If you have a potential difference between the ends of a conductor, you have some resistance in the wire, right? And you can represent that like this. And in the same way, we can apply the same analysis to the thermal resistance in the wall. So if we look at the question that we have been given, we're going to have convective heat flow or loss on this side. And there's going to be some resistance between the foam and the air contained on this side of the wall. Okay, so we have some resistance at this point. And between the foam and the wall and the plaster on the inner side, you have some form of resistance. You have some form of resistance in the brick and the plasters in this cross section here. Okay. And then finally, the plaster on the outside side, on the outside of the wall, and then between the plaster and the outside air. Okay, so let's try and represent these thermal resistances in a circuit so that we can further analyze what we have. So let's say we have temperature coming in, some form of heat loss or gain coming in, right? And then we have our first thermal resistance. Okay, I'll call this R. Let me call this R inside. Okay. And then I may run out of space. This way. Okay, so we have T infinity, because we don't know where that region exists. And then we have Ri. And then we have, I'll call this R1, which is the thermal resistance in the foam. Okay. And then after that, we're going to have another thermal resistance. I'll call this R2, which is the outside plaster. Now, up until this point, we have these surface areas existing. It's a homogeneous material in this point. But by the time we get to this region, it's no longer homogeneous. Okay, we have multiple materials. Okay, so we have to, there's a way of evaluating a region in the wall where you don't have one material. And I'm hoping that you've done this in class. Okay, it's similar to the parallel arrangement of resistors in an electric circuit. Okay, so we have um, considering, let's assume that we're considering the heat flow through this region, okay? Because we could have as many as, if you're looking at, the question says we have a 6 meter wide wall, okay? So if we consider the entire 6 meters of the wall, the number of thermal resistance that we will have in parallel could be significant, okay? And if we want to simplify this problem, we have to consider a region in the wall. Now, if you do the math for the entire 6 meter wide wall and you compute the same thing for a section of the wall, you will get the same result because it's a ratio. So I'm just going to pick a region in the wall where we have a plaster, we have a plaster, a brick, and then another plaster region, just so that we have that covered. If you multiply that by uh, the rest of the portion of the wall, you get the same result. So this is going to split into three resistances. Yeah. So I'll call this R3, R4, and R5. And then we have the outside plaster region. I'll call this R6. And then we have the final one, which is the convective thermal resistance to the outside, right? And then I'll call this RO. So evaluating this will give us the equivalent resistance for the entire wall. Okay. Now, this is the portion of the question where you might have some confusion on how to evaluate. So I'm going to pick this part of the question and solve it, and then you have to do the rest for your assignment. Now, to solve this, the conduction thermal resistance is simply given by this formula. I'm sure you have solved the derivation for this in class. Is a length divided by the thermal resistance for the material multiplied by the area. And then the convective thermal resistance, R convection, is equal to 1 over HA. And in the given question, these are the two types of thermal resistances that we are going to encounter. Well, if you look at the case that we're dealing with, we only have um, conduction thermal resistance to deal with. Okay, we don't have any convective thermal resistance in this region. Now, so to find the equivalent of R345, this is what we're trying to find, because the other ones we have are pretty straightforward. I'm assuming you can evaluate that on your own. Now for R3, let us deal with R4 first. Okay, and then we'll do, because R3, it's R3 and R5 pretty much the same. So you just have to evaluate one of them and you find the other. Now, R4 is a thermal resistance through the brick. This brick we have here. Now, this portion that I have coded out to do the analysis with is equivalent to 1 meter by 0.33 meters wide portion of the wall. Okay, sorry, 1 meter by 0.33 meters. 1 meter by 0.33 meters. Now, if you pick 1 meter by 0.33 meters and you evaluate it, you get a ratio. It's the same ratio that applies if you consider the entire wall. Okay, if we count the number of bricks, you will have an entire 6 meter by 4 meter wall, and divided by these areas and thermal resistances, you get the same ratio. So for R4, I'll write this here. Equal to the length of the brick divided by K multiplied by A. And we have been given K in the question for the brick to be 0.72 watts per meter degree Celsius. So if we do that now remember that we have been given the length of the brick to be 18 centimeters, right? 18 cm is the length of the brick. I'm going to try and convert that to standard units because everything has to be in the same units, and that will simply give us 0.18 meters. And then divide that by 0.72 watts per meter degree Celsius. Okay. And then multiply that by the area of the brick, which will be, remember that I said I'm considering 1 meter by 1 meter by 0.33 meters. Okay. So if we evaluate that now, the area that is covered by the brick in this expression is 0.33 times, I'm running out of space, by 1 meter squared. So the thermal resistance for the brick will now come to 0.833 degrees Celsius per watt. So this is it's a ratio. Okay, for every wattage, you get 0.833 degrees Celsius thermal resistance. Okay, so that's for R4 now. So for R3 and R5, R3 and R5 are going to be the same. Here. For the length of wall that we have, they're both equal. And now if you look at this question, the amount of heat, the heat resistance that comes with the side of this, what we had as R6, okay, depends on the thermal conductivity of the convective heat coming from the outside. Okay. Now the thermal conductivity, the thermal convective heat, the thermal heat convection from the outside, the rate at which it enters this side plaster will be transferred to whatever it touches on the inside. Okay. So there's a dependence on H for R6. Now, if you balance out the thermal conductivities through this wall, they kind of depend on each other. Okay, so instead of dividing this by the thermal conductivity for that's K, we'll divide it by H outside. I hope that makes sense to you. So for R5 and R6, R3 and R5 will depend on H outside. Okay. So in our expression, we're going to have L over H outside multiplied by A. Okay. So once again, for the 1 meter by 0.33 meter portion of wall that I have cordoned off and I'm trying to analyze, I'm going to, oh, I made a mistake in the calculation. Hold on. So this is 0.3, not 0.33. Let me write this out properly just so you don't get confused. Let me write this out again, the R4. So R4 is equal to L over KA. Okay, we know the length of the break to be 0.18 meter, that is 18 centimeters, divided by 0.72 watts per meter degrees Celsius, okay, multiplied by 0.3 meter times 1 meter squared. Now, we're considering a region in the wall of 1 meter by 0.33 meter. Okay, that's the region in the wall where you have one break. Okay, but however, we have the wall to be 1 meter wide. So I'm multiplying it by the length of one break. Remember that one break is given to be 30 cm long. Okay. So I'm taking the length of one break and I'm multiplying it by the width of the wall that I have chosen. If I decided to consider the entire wall, then I'll multiply the length of one break by the entire length of the wall, width of the wall. Now don't get confused, okay? If you want to go ahead and evaluate this for the entire wall, you multiply the length of one break by the entire length of the wall. Okay? So this is 0.3 meters multiplied by the entire portion of the wall that we're considering. Okay. So sorry about that. This is 0.3. Now, in the same way, we are going to pick the portion of the plaster, that's R3 and R5, that is covered in the section of wall that we have taken into consideration. Okay, so we have that R3 is equal to R5 equal to L over H outside multiplied by the area. And we're given the length of the plaster to be 1.5 cm, right? So which means that we will have the length to be 0.015 meter divided by, we're given H outside to be 20 watts, 0.2. 20 watts per meter Kelvin. Okay. And then multiply this by um, 0. Oh, sorry. The length of our plaster is, hold on, 2 cm. The length of our plaster is going to be the same as the length of the brick. No. So this is the length of our plaster, right? This is this is the one that we have to multiply by the length of the wall that we're considering, 1.5 cm multiplied by the amount of wall that we're considering, and then this is the width that we are dividing. This is the length, and it's the same with the length of our brick. So sorry, this is 0.18 meter divided by 20 watts per meter Kelvin multiplied by 0.5 times 1 meter squared. Okay, I hope if you're confused, please let me know so I can go over that again. Okay, and if you evaluate that, you get 0.18 get 0.6. 0.6 degrees Celsius per watt. Okay. So now that we have R4 and R3 and R5, we can go ahead and now compute the do the parallel computation, okay, for the middle part of our wall. So if we have 1 over the equivalent R for the middle part, right? Once again, if you remember how to evaluate the resistances in an electric circuit, it's the same thing. You apply the same analysis. So we have 1 over R3 plus 1 over R4 plus 1 over R5. Okay. And we have our R4 to be 0.833. We have R3 to be 0.6. So we get 1 over 0.6 plus 1 over 0.833 plus 1 over 0.6. Okay. And then if we now evaluate this, add all these 3 fractions together, one over 6, 1 over 0.6, plus 1.833. Okay, and then we take, this is equal to 4.5. Okay. So we're going to have to take the inverse of that. Okay. 0.220 degrees Celsius per watt. Okay. So if you I wish we had more time so we can go ahead and try this with the full length of the wall just to see if we get the same answer for the middle part of our wall. Okay. Hold on. Oh, I'm sorry, guys. I'm seeing some mistakes in my analysis. You know what? Let me do that again. So we have R4 is equal to L over KA, and this is equal to 0.18 meters, which is 18 centimeters, the length of our brick, the thickness of our brick rather, 0.72 watts per meter Kelvin times 0.3, which is the length of each brick multiplied by 1.1 meter square, right? I think this is pretty correct. 833 degrees Celsius per watt. Now for R3 and R5, well, looking at this, I think it's correct if we use K rather than H, because this does not touch the outside air, okay, and it's more in contact with the foam than the outside air. So I would say, okay, just scrap this, okay. Sorry about that. Forgive me for that. This is L equals to KA, because I just saw now in the question that we've been given a special K for the plaster. Okay. Sorry about that, guys. So if you aren't given K for the material, then you have to assume that heat is the same amount of thermal resistance is coming from the material closest to it. But we have a K for the plaster layers. Okay. So it means that, and also the length of each plaster layer is 3.3 cm thick. Okay, so which means each one is 1.5. The ones on the sides are 2 cm thick. Okay, so the thickness is, I'll still go with um, um, 0.18 because I'm considering this region. Okay, and it has the same length as a brick. So 0.18 meter for the plaster, and then we use the K that is given for the plaster layer, which is 0.22 watts per meter Kelvin or Celsius, whichever one is correct. And then multiply that by the length of the plaster, which is 0.015 if you convert it to meters, multiplied by 1 meter squared. Okay, I think this is the correct way to do it. Please don't forget to make the correction. Okay, so if you multiply this now, we get 0.15 multiplied by 1, we get 0.015 multiplied by 0.22, and then divide all this now by divide 0.18 by everything we have. Okay, so we get 54.55 degrees Celsius per watt. So this actually sounds more accurate, okay? Yeah, because I was getting worried about the small value we got. This sounds more accurate considering that we have a very small amount of plaster as compared to the brick. Okay, so this is our R3 and R5. So the R equivalent, 1 over the R equivalent for the middle region will now be equal to 1 over 54.55 plus 1 over 0.833 plus 1 over 54.55. Remember, the reason why we're doing this is the equivalent resistance for resistors in parallel. You evaluate them like this, right? So it's something similar to that. So if we add these three values, we get 1 over 54.55 plus 1 over 0.8 plus okay, we get 1.24. Let's take the inverse so that we'll find the value of R equivalent. Okay, I'll take the inverse of that, and you get 0.8083 degrees Celsius per watt. Okay, so this is your R345 value. Okay. Please, I made a lot of mistakes in solving this question. If you have any confusion, please let me know so I'll go over it again. Okay. I hope you understand how we arrived at this result. You pick a portion of wall, okay, find out how many bricks you're going to have in that portion of wall. Now, I want to have um, um, 1 meter square portion of wall, okay, and then I did the analysis and I got this value for R35. Now, if you want to go ahead and, because all you have to do to get the equivalent resistance for the rest of your circuit is just find the thermal resistance in the other part of the circuit, and then it's a simple addition. Now, in order for this result to match what we have here, you have to also consider these as 1 meter square by 0.33. Okay. If you do the analysis for the rest of the wall using the full value that you have in the question, you add it to the final results you have here, you'll be modeling something different. Okay. So in the same way, you consider the thermal heat resistance, the convective heat resistance coming to the foam, assuming that the foam is 1 meter square by 0.33 meter, 1 meter by 0.33 meter in area, right? You consider the thermal conductive heat resistance between the foam and the outside plaster. Okay. And then the plaster and the inside combination of brick and plaster. And then you do that for the brick and plaster in the middle and the outside plaster. And then the outside plaster and the outside air. Now, if you do all that with this same size of wall and then add it to the final value you have here, you get the combined resistance for the entire wall. Okay. Please, I want someone to ask me a question because I hope if you don't ask me a question, it means that you understand everything I've said despite the back and forth. So is it clear? Do you understand this? Okay. So we have one more question to solve today. Okay, so this question says, let me get a fresh piece of paper. Superheated steam at an average temperature 200 degrees Celsius is transported through a steel pipe. Okay, and these are the dimensions for the pipe. This is the thermal conductivity of the material in the pipe, the outside diameter, inside diameter, and the length of the pipe. The pipe is insulated with a 4 cm thick layer of gypsum plaster. Okay, and that is the thermal conductivity for the plaster. The insulated pipe is placed horizontally inside the warehouse, where the average air temperature is 10 degrees Celsius. That will be the air surrounding the pipe. The steam and the air heat transfer coefficients are estimated to be 800 and 200 watts per meter square Kelvin, respectively. I'll calculate the daily rate of heat transfer from the superheated steam and the temperature on the outside surface of the gypsum plaster insulation. Okay, so let me draw that out real quick. Okay, so from the question, we have cylindrical pipe. And this cylindrical pipe has insulation on the outside. Okay, let's say this is the insulation. And then we have the pipe inside. Now, we have another problem where in order to evaluate this problem, we have to find the equivalent thermal resistances in the entire system. Okay. So first of all, we have air. Let me start from inside out. So we have a temperature inside, which is going to make contact with the inside parts of the wall, right? Call that R1. And then now from the inside part of the cylinder, the internal parts, heat is going to be gained or lost by convection. So I'll just name this R inside. And then this will be the thermal resistance of the steel pipe. I'll call that R1. And then from the steel pipe, heat is going to be gained or lost into the insulation on the outside. I'll call that R2. And then from the insulation on the inside, we are going to have R outside. Okay, so in order to find the equivalent resistance for the entire pipe, we have to evaluate this. Now, Ri, oh, sorry guys, this class is supposed to end at 8:50. Oh, do you want me to go ahead and finish this real quick, or I don't know? Since
I have to leave here in a sec. But
you feel free, please. Okay.
Also, did you take attendance this morning?
No,
I wasn't
no,
here. Okay.
no, we're not taking attendance. Okay.
Okay. Yeah, I wasn't here at the start of the class.
Oh, okay. Yeah, so there's going to be a recording of the class on Moodle. If you want to come back and refer to something I said, okay, you can always do that. And yeah, feel free to leave. I'm just going to quickly rush through this, okay, so that you, for those of you that want to refer to this, okay. So Ri, we already talked about, is 1 over HA, right? And then R, this is a conductive, you're going to have to evaluate this conductively. And since we're dealing with cylindrical, we cannot accurately analyze this with Cartesian coordinates. Remember that what we talked about last week, if you're considering it through a wall, then Cartesian analysis of Fourier's heat law of conduction is the best way to go. If you use Cartesian with cylindrical problem, you will not be modeling the correct thing. Okay, and I didn't talk about this earlier. The equivalent thermal resistance for conduction through cylindrical axis is equal to natural log of divided by 2 pi k L. Okay. I hope that makes sense to you. Okay, so now we have yeah, so we have that. We're going to have then the outside over d in over 2 pi KL. That will be for R1. And then for R2, we'll have the same thing, just for a different set of diameter values. 2 pi KL. And then the R outside is also going to be the interaction between the outside insulation and the outside air. Okay, so if you follow this, you'll be able to get the equivalent resistance through the cylinder. Okay. Yeah. So and from there, once you get this value, evaluating Q shouldn't be a problem if you follow the same instructions as we have done before. So it's almost 9 o'clock. So in fairness to the others, I think I'll just go ahead and end today's class. Thanks, guys, for staying, and please take note of the correction I made for the solution to the equivalent resistance in the middle part of the wall. Okay, and sorry about all that. So have a nice rest of your day, and I'll see you guys next week. Thank you.
Thank you.
Yeah.
Have a good day.
You too. Thank you.